Wonderful children, I am here with the one and only Mr. Klein, which is why I'm all masked up. What's up, Mr. Klein?
What's up, everyone?
Woo! It's my new Taco Thursday mask here. Tacos make me happy. So it actually works out perfect because I get to flex the mask in the video. Let's get it. Parametric equations. Now, parametric equations are pretty fantastic if you ask me, although I do think everything in math is fantastic. So basically, it's like we're putting a couple equations together, okay? We're restricted by some parameters, often time, which is why we'll usually use t for that, okay? So that's like our third variable there. So I'm going to hop down here to our first example. So we want to graph the curve defined by the parametric equations and indicate the direction. So we are going to add like little arrows along the path, okay? And then we're going to convert it to rectangular form. So I have an equation for x, okay? X equals t. Then I have y equals t cubed. And then I have a domain restriction for t here from 0 to 3. So you ever remember those problems from Algebra 2 where they say like you threw a ball in the air or some projectile or whatever it might have been. Here's the height as a function of time. And you graphed it and you kind of thought that like, oh, that's the path of the ball. That was not the path of the ball. That was its height as time passed. Now we're going to be able to take that height as a function of time, and we're going to be able to take its distance that it's traveled as a function of time. Put those two together, and with parametric equations, we can actually plot the path that projectile, that ball, or whatever, actually makes. This is the moment you've all been waiting for. Not today, though. The next day will be the application. Look at that. Look at that. I teased you there. Okay, let's get to it. So, since the domain restriction for t is 0 to 3, I will just go ahead and... froze. Oh, there we go. All right. We're back. Let's see if that happens again. Froze a little. All right. So I go 0, 1, 2, and 3. Awesome. So let's find our x values. So if I plug 0 in for t, I would just get 0 for x. If I plug 1 in, I'd get 1, 2, I'd get 2, and 3, I'd get 3. And then for y, well, 0 cubed is still 0, 1 cubed is still 1, but 2 cubed is 8, and then 27. And what we end up getting are these ordered pairs, these x and y ordered pairs, 0, 0, 1, 1, 2, 8, and 3, 27. Cool. So let's go ahead and plot this. I'm going to scale out while I pause the video. All right, so we have 0, 0, we have 1, 1, and I obviously didn't notch them all out, but I tried to be a little more drastic as we made those jumps. It's not perfectly to scale, but it does the trick. And I have this right here. Now, I do want to know, or pop some arrows on there showing the direction that this thing is traveling, right? Because that's the path that whatever this is taking, okay, as time goes from 0 to 3. All right? Well, there we go. So that path, those arrows show the path that it's taken that is important here. We want to make sure that we have those. So let's talk domain and range here. So domain is still restricted from 0 to 3. Those are my x values, right? So from 0, oops, that's a 2 there, 0 to 3, including it. And then my range, that's going to be from 0 to 27 for my parametric equation here. Now we want to convert it to rectangular. There's a couple ways of going about this. So I've already got x solved for t, right? So what I can do is I can just substitute that into my y function. So substitute. And I will get y is equal to x cubed. That one's pretty simple. They're not always that way. Okay, we could have solved for t in the y one by doing cube root, but that just seems kind of silly and not really that helpful. So we went the easier route here. So x is equal to t. Directly substitute in x in there for t into that function. Boom. We've got it in rectangular. And that does look like a portion of a cubic function. You know, usually a cubic function would then come back down this way as well. But we have that domain restriction. All right. Look at that. First example. Dunzo. Raise the roof. Are you raising the roof, Mr. Klein?
Raising it.
He's raising it. He's raising it. I saw it. All right. Example 2 time. All right, so same kind of example here, very generic. Again, we're going to get into application here soon, but we're just getting some of the nitty-gritty done here, the mechanics done of this one. So here we've got Again, we're going to graph the curve defined by the parametric equations. We're going to indicate the direction by putting those little arrows on there, and we're going to convert to rectangular form. So I've got what my x equals, what my y equals, and then I have t is greater than or equal to -2. So let's go with like -2, -1, 0, 1, 2, and it would go on and on because there's no upper bound there. But we'll stop. I don't have time to go on and on, right? I don't have time for that. Okay, so if I plug -2 in for t with the x, I'd end up getting 4 times 3 is 12. If I plug -1 in, I'm going to get 3 times 1 is 3. 0 would give me 0. 1 would give me 3. And then I would end up with 12 again. And that makes sense there because that's like quadratic, right? It's going to be symmetrical there. Okay. Now, how about for y? If I plug in -2, I'm going to get -4. For -1, I'm going to get -2. 0, I'm going to get 0. 1 will give me 2. And then 2 will give me 4. So I've got these ordered pairs of 12, -4. And this is, again, what I'm going to plot. 0, 0, 3, 2, and then 12, 4. So again, let's go ahead and scale accordingly. All right, I put the necessary ones there. So if I have 12, -4, that puts me right down here. And this is our start. Maybe I'll write that so I don't forget. And then I've got 3, -2, which would be right here. And then 0, 0. And then 3, 2. And then 12, 4. So I've got this sideways parabola looking dealio here. It will keep going there. And I'll put some arrows showing its path, as we said we would do. All right, there we go. I guess I don't really need that last one. That shows me the path, right? Shows me what direction we're going there. Awesome. Graph, check. Domain time. Domain. So my domain would be from... what's the lowest my x value gets? That's going to be 0. And again, remember, it keeps going on and on, right? It keeps going on. So I'd have 3, 4, 5, 6 for my t. So that would keep going. And I'll end up with from 0 to infinity. And then my range, what's the lowest the range goes? That would be -4. And that, because it continues to go on, right? It's not capped at 2 for my t values. They would keep going. We just aren't graphing them out. That will be infinity as well. Domain and range. Donezo. We're talking about the domain and range of that parametric function. Okay. Convert to rectangular. So this one's not like the easy, like, oh, something's already solved, right? So we got to go one of two routes here. We can do, and I'm going to show you guys both of them. Okay, so if I have x is equal to 3t squared and y is equal to 2t, first one I'm going to do is I'm going to solve the y one. That one looks easy, right? So I'd have t is equal to y divided by 2. Now I can sub that in, sub into the x. So I'd have x is equal to 3 y over 2 squared. All right. Now, if I distribute that squared, I get y squared over 4. So really my final here is 3 over 4 y squared if I were to simplify that. So that's rectangular form. That's good to go. I could also go the other route. So if I were to solve the x one, I'll do that in a different color. So I'll be using green for a while here. I'll go purple. It was a top-rated Expo marker color in class today in our class question of the day. Purple Expo markers. I don't have any of those. I should get some. Mr. Klein, do you have any purple Expo markers?
No.
No. Okay, they're rare, but they're the fave. Got to get some. All right, so if I solve x, that x one, if I isolate t, first I'd have to do is I'll write them all down here. Divide by 3. So you get x over 3 equals t squared. Square root on both sides. So I'd get t equals plus or minus the square root of x over 3. Cool. Now I can take that and I can plug it into my y. So I'll go subs. And I'll have y equals, and then it'll be, that plus or minus, I'll pop that up front, 2 square root x over 3. Now, if this is like a final answer with like solutions and things, we would rationalize the denominator. I'm going to leave it like that. Honestly, it'd be a lot easier just using this green one here, right? A little cleaner, yeah? It makes sense that that's the equation to do. It's like the sideways parabola, which is usually where the x is the linear one, then we have the y is the quadratic, right? That's what we remember that from Algebra 2. Cool. We should remember it from Algebra 2. Awesome sauce. We got it all. We got it all. Now that we've tackled a bit of the handwriting aspect of it, let's get into our graphing calculator. So bust out them TI-84s, you know. Yo-ro. Always gotta rep the yo-ro. And we're going to go into a different mode here, okay? So if we turn ours on, you know, my emulator here, it turns off to save its battery. Go to mode. And you're going to arrow down, and where you see normally we'd be in function or we'd be in polar mode from what we've done in class so far, we're going to choose parametric. There's just not enough room to write parametric there. So you're going to select that one here, and we're going to head over to our y equals, and as you see, I already plugged it in to save a little time here. In your x1, you're going to put in 3t squared. I got that t from just hitting my normal variable button key, okay? See how it says xt theta n? Theta was when we were in polar, x is when we're in function mode. So t, there we go. N will be for sequences. Yes, you will use all 4 this year. That's awesome. All right, for y, we've got 2t. Lovely. Now that we got that all plugged in, let's head over to our window and we'll adjust so we have the exact same window. As you can see, I already did that, so feel free to pause the video to mimic that window that we have there. In this one here, it says the interval is going to be -2 is less than or equal to t, which is less than or equal to 2. So they are limiting it to stop at 2 for this particular problem. Now, okay, so with this adjusted problem, we're going to limit that. We're going to put an upper bound. All right. Once you got that all plugged in, we'll move on. So pause if you need to. All righty. So now let's graph. Beautiful. So yours should look something like this. Now, I'm going to try to get this out of the way here, but I can't. So that t step, where it was 0.1, that's just telling it how many points to plot. So it would start at -2, and then -1.9, and then -1.8, so on and so forth. So that's just telling you how many times to plot those points there. All right, so that's how you graph parametrics. That's all we're going to do with that. Pretty handy little thing there. We'll work more with it later on, especially when we get to applications. All right. Let's keep moving. All right. For this next one here, we're going to, there we go. We're going to convert to rectangular. That's all we're doing here. And then we're going to sketch it on our calculator to check, see if it the equation you're going to get is something pretty familiar to you. You'll see that it's like, hey man, that's legit. All right. So I am going to solve that top one, the x equals. I'm going to solve that for t. That one looks like the easiest approach. And it's also, I'm going to be able to have like y equals something then, which is obviously also easier for graphing as well. So I'm going to have x equals -t plus 2. I'll go ahead and subtract 2, so I get x minus 2 is equal to -t. If I divide by -1, I'm going to get -x plus 2 equals t. So that's going to get substituted in, and I'll have y, I'll change colors here, y equals -x plus 2 squared minus 4. All right. Very good. So it looks like we're going to have a parabola of sorts. So let's go ahead and plug that into our graphing calculator. All right. So we got in our calculator here, -t plus 2 for x. We got t squared minus 4 for y. In my window, I decided to change it a little. So I did -1 to 4 because that's what it said there in the problem, that we were going to restrict t to -1 to 4. I changed my x max and I had to change my x minimum. We'll go like -5 as well. And I'm going to change my y max a little bit. I'm going to change that to like 15. So let's graph this. Okay. Very nice. I like it. Cool. So as you can see, that is like a portion of a parabola, right? And that is a quadratic that we have there. Once we converted it into rectangular. That all checks out. That looks legit. I like it. Very good. Wonderful and fantastic. Yeah, you'll notice that the vertex looks like it's right here at like +2, -4. And if you were to factor out that -1 from the x, it'd become a x minus 2 in parentheses. So it is a shift to the right 2, if you remember your transformations. Got to tie it all in here. Tie it all in. Good stuff. All right. Let's move on to example 4, shall we? I think we shall. All right, so this one gets a little cray here at the end. I think you're going to enjoy it thoroughly. So we have curved movement represented with cosine and with sine. We want to graph and convert to rectangular form. So we're going from 0 to pi. How about we do some of our familiar trig values? How about 0? We'll go pi over 2 and pi. So now if I plug in 0 for cosine of 0 is 1. 1 times 5 is 5. Cosine of pi over 2, that's going to be 0 times 5 is 0. And then for pi, that'd be negative 1 times 5 is negative 5. Lovely. Now for sine, if I plug in 0, I get 0. If I plug pi over 2 in, I get 1 times 3 is 3. And then for pi, it's 0 again, times 3 is 0. So I've got my ordered pairs of 5, 0, 0, 3, negative 5, 0. Okay. All right. Well, let's go ahead and graph this thing, shall we? So we'd have something like 5 out here, and then we'd have 0, 3, and then negative 5 here. It's going to start here, kind of like half of an ovally looking shape, perhaps a little ellipsy part of it, right? If I were to curve that a little better down here at the start. Definitely not doesn't look like it would necessarily be a circle, right? Because it's not even, but I mean, who knows? Maybe there's more to it than we know. Let's see here. How about we convert now to rectangular form? No, this was going to be a curveball out of left field for you to be like, okay, well, how the heck am I going to do that? Like, am I going to use like inverse trig, but then like that's messy? How about this? Ready? I'm gonna throw one at you here. So let's say we could square both sides of an equation, right? So bear with me. If I square both sides of the equation, I've got a cosine squared and a sine squared. And when we're dealing with systems of equations, because we've been doing substitution, right? If you were to add your equations together, kind of like you do for elimination method, well, if I have a cosine squared and a sine squared, when I add those together, I get a 1. Okay? So I want to jot that down. Cosine squared theta plus sine squared theta is equal to 1. Or in this case, we have t, right? So let's go ahead, and I'm going to take x equals 5 cosine t. I'm going to square both sides. So I get x squared equals 25 cosine squared t. And I'm going to do the same thing for y. So I get y equals 3 sine t. I'm going to square both sides. And I get y squared is equal to 9 sine squared t. Okay. Everything we've done so far is totally math legal, right? This is cool. We're good. It's okay. It's wonderful. Okay. Now, I'm going to come over here, give us a little more room to work with a fresh color. I'm going to go with red. Okay. I'm going to get cosine squared by itself. So I'd have x squared divided by 25 is equal to cosine squared t. And I'll do the same thing for the y here. Y squared divided by 9 is equal to sine squared t. If I add these two equations together, each side, I'm going to get cosine squared plus sine squared is equal to 1, right? And then I'll keep these guys separate. Holy guacamole, Taco Thursday. Yes, I waited till now, the end of the video, to say that. This right here is the equation of an ellipse centered at 0, 0, right? With a major axis of 5 and a minor axis of 3. Well, hot diggity dang, we certainly had something representing that in blue there. Major axis of 5, or with the going from 5 out, right? The whole length would be 10. And then we have our minor going up 3, down 3, so full length of 6. That's what I'm talking about. That was cool. That one, I mean, I wouldn't think that we would think about that one on our own necessarily, that the manipulation we did there with squaring both sides, thinking that far ahead to then add the cosine and sine together to give us 1, right, using our Pythagorean identities. But it is all math legal and legit, right? No one's going to math jail here. We are good to go. Awesome. Fantastic. So that's it. That's it for day 1 here. We're going to get into applications in day 2. But we just want to go through the mechanics of the whole thing today. Hope you guys enjoyed it. America, freedom, rock and roll, Costco, Yo-Ro, Riverdog Jenny on the gram. Shout out to Mr. Klein for being here, listening to me babble about parametric equations just like you guys did right now. See ya.